today's session we are going to cover the equipotential lines and the electric field mapping. But before we tackle that part, we are first going to introduce a concept which is essential in our topic of today, which is the electrostatics. So what do we understand by the electrostatics? The electrostatics is by definition the study of stationary electric charges. So electrostatics is actually the study of stationary electric charges, whether it's a positive or a negative electric charge. So in other words, electrostatics is actually the study of electricity at rest. And such concept of electrostatics is actually quite the opposite of the electrical current concept, which is based upon the study of the flow of electrons or the study of electrons in motion. So electrostatics is actually a different concept than the electrical current. So the electrical current is basically based upon the study of the flow of electrons, whereas electrostatics is actually based upon the study of static electricity. So in that case, we can distinguish two types of electrostatic charges. We can distinguish the protons, or simply the positive charges, and we can distinguish the electrons, which are simply the negative charges. So based on that, we can actually distinguish three different cases. A case where we might have a positively charged object, a case where we might have a negatively charged object, and another case where we might have an electrically neutral object. So for example, if we consider the following object, which has a proton bounded to an electron, another electron bounded to another proton, and then we have a bunch of stray protons over here. Therefore, as we can see, we have more protons in that object than we have electrons. Therefore, such object is characterized to be positively charged. Now, if we consider another object where we have an electron bound to a proton, another electron bound to another proton, but then we have a bunch of stray electrons. Therefore, over here we have an abundance of electrons and a deficiency in protons in that object. Therefore, such object is characterized to be negatively charged. And finally, we have the third case where the number of protons in a material, it actually equates the number of electrons. Therefore, they are balancing each other out. And in that case, we characterize such material to be an electrically neutral material. So we have the third case where we have a proton bound to an electron, another electron bound to another proton, so on and so forth. So as we can see over here, the electrons and the protons, they are balancing each other out. Therefore, such material is characterized to be electrically neutral material. Now let's consider that we bring, in the vicinity of that material, we bring a charged object. Let's consider that we bring over here a charged object. It doesn't matter if it's actually positively or negatively charged. Let's consider that we have a certain charged object. We are going to suppose it is actually positively charged, and we bring it in the vicinity of that electrically neutral material. So what's going to happen in that case? That charged object, upon bringing it at a close distance from that electrically neutral material, is going to induce into it a new charge distribution. So that object is going to induce in that material a new charge distribution, meaning that the electrons are going to be attracted by that positively charged object, and they are going to occupy the left side part of that object, whereas the protons are going to be repelled by that positively charged object, and they are going to occupy the right side part of that material. So in other words, that material over here is going to become polarized, meaning now it has a polarity. It has a negative polarity and a positive polarity. So in that case, we are going to have the following charge distribution within that material: the negative charge the negative charges, or the electrons are going to occupy the left side, whereas the positive charges are going to be occupying the right side of that material. So over here, such material now is characterized to be polarized, meaning now it has a polarity. It has a negative polarity and a positive polarity. However, the act of inducing a new charge distribution within a material, it actually requires forces. And more specifically, it requires two forces. It requires an attractive force and a repulsive force. So, inducing a new charge distribution within an object, it requires two forces, which are what? These two forces are a repulsive force and an attractive force. So, these two forces, the nature of these two forces is actually electrical. So the repulsive force and attractive force, they are actually electric forces. Moreover, the magnitude or the impact or the strength of these two forces is actually dependent upon their presence from the source charge, meaning that if you move away from the source charge, therefore the intensity or the strength of these two forces is going to decrease as a function of distance. As you move away from source charge, the intensity of these two forces is going to decay as a function of distance. And this is actually related to the fact that the electric field of that main charge is also going to decrease as you move away from the source charge. Which brings us to our topic of today, the electric field. So what do we understand by the electric field? How can we define the electric field? And what would be the directionality of the electric field in addition to defining the strength of an electric field? Now moving on to the electric field. So what do we understand by the electric field? The electric field is defined as a region of energy which is present around a charge. And that region of energy, or the effect of that region of energy, it can be felt by any other charge placed nearby. So the electric field is defined as a region of energy which is present around a charge, an electric charge. And the effect of that region of energy, it actually can be felt by any other charge placed nearby. For example, if we consider the following charge Q, it can be positive or negative, it doesn't matter. The charge Q is going to create all around it a certain region of energy. And the region of energy we are going to label it to be as an electric field region. So the charge Q over here, whether it's positive or negative, it's going to create or to produce a region of energy all around it, which we are going to refer to it as the electric field region. If you notice over here, I have actually indicated the periphery of that electric field region with dotted lines. And that in order to imply that the reach of the electric field which is generated by Q is actually limited. And therefore the reach of that electric field which is generated by Q, it actually depends directly on the strength of Q. So in order for that limit to stretch further beyond, the strength of Q, it has to be greater. So the greater the strength of Q is, therefore that limit is going to stretch further beyond. Whereas if Q over here, or the strength of Q, is actually weaker, therefore the limit of that electric field region is going to be narrower. So the reach is going to be dependent directly on the strength of Q. For example, if you consider a certain charge Q prime to be placed outside of that electric field region, therefore that charge Q prime is not going to feel the effect of the electric field which is actually generated by Q. Now let's consider a case where we have a certain charge Q2 placed within that electric field region, and over here we are going to name that charge Q1. Q2 and Q1, they are actually separated by a certain distance r, and we are going to consider furthermore that both charges are actually positive. Now in that case, since Q2 is actually present within an electric field region that is generated by Q1, therefore Q2 is going to feel the effect of an electric force exerted on it by Q1. So Q1 is going to exert an electric force on Q2, which is going to be directed that way. And that force will be called F of Q1 on Q2, which is the force exerted by Q1 on Q2. In a similar manner, Q1 is going to feel the effect of a force exerted on it by Q2. So Q2 is going to exert also an electric force on Q1, which is going to be directed that way. And that would be F of Q2 on Q1. And as we can see, these two forces, they actually repel. And this is because we have like charges over here. We have two positive charges. And even if we had negative charges, these two forces are going to repel each other. Now, if we had opposite charges, negative and positive, therefore these two forces would have been directed inwardly. Now, the nature of these two forces is actually electrical, and moreover, they are repulsive forces. So over here we have two electrical repulsive forces. Now regarding the expression of these two forces, or the strength of these two forces. Mathematically, the expression of an electric force is actually given by Coulomb's law to be, so let me write it over here. So the strength, or the expression of an electric force is actually given by Coulomb's law to be F equal to K, which is Coulomb's constant, multiplied by Q1, multiplied by Q2 over the separation squared. So as we can see over here, the electric force is directly proportional to the product of these two charges, and it's also proportional to K. And K in that case is labeled to be Coulomb's constant, which is equal to 1 over 4 pi epsilon 0. So what would be the epsilon in that case? The epsilon 0 in that case is none other but the permittivity of free space. So the permittivity of free space is actually an indication of the ability of free space to support an electric field. So over here we have that force F being directly related to that Coulomb's constant and directly related to the product between these two charges between which that force is actually applied. In addition, that force F is actually proportional to what? It is proportional to the inverse of the separation squared. Meaning that whenever you move away from either of these two charges, therefore the strength of that force F is actually going to decrease as a function of 1 over the distance squared, or 1 over the separation squared. And that would be the equation for the electric force. Now regarding the derivation of that equation, it is actually derived from Maxwell's equation and from Gauss' law. But I suppose that you haven't seen any of these two laws yet. So we are going to leave the calculus behind that equation to a later time until you have actually studied Gauss' law and you have seen Maxwell's equations. Now after introducing that force over here, the electric force, we can also distinguish the fact that source charge Q1, it is also going to produce a very specific electric field at point Q2. So besides the fact that Q1 is actually exerting an electric force at Q2, Q1 is also producing a certain electric field at point Q2. So for example, if we consider random points in that electric field region over here, Q1 is going to be producing at each one of these points a certain electric field. And of course, the strength of that electric field is going to vary from one point to another because, as we are going to see later on, it's going to be dependent on distance. In addition, Q1 is going to be actually producing at point Q2 over here a very specific electric field. And that electric field in that case, or the strength of that electric field at point Q2 is going to be equal to the force exerted on Q2 per unit charge of Q2. So in that case, the strength of the electric field is going to be equal to the force exerted on Q2 per unit charge of Q2. So in other words, E is equal to F of Q1 on Q2 over Q2, which is equal to 1 over 4 pi epsilon 0 times Q1 times Q2 over Q2 times 1 over R squared. So over here we can simplify the common terms, Q2 and Q2, and finally we are left with that the equation for the electric field is given as 1 over 4 pi epsilon 0 times Q1 over R squared. And that would be the final expression for the strength of the electric field, which has a unit of newtons per coulomb. So over here, if we look at that expression, we can clearly see that, first off, the strength of that electric field is directly related to the strength of the source charge, which is actually producing that electric field. So the source charge in that case would be Q1, which is producing that electric field at point Q2. So as we can see, they are directly related to each other. Moreover, that electric field is actually proportional to the inverse of the distance squared. So that electric field is proportional to 1 over R squared, meaning that as you move away from Q1, the strength of that electric field is going to decay as a function of 1 over R squared. Now moving on to the directionality of the electric field. Now the electric field is always directed from a positive charge towards a negative one, meaning that it emanates from a positive charge and it terminates on a negative one. So if we consider a single positive charge Q, therefore the electric field is going to be emanating in all directions from that charge and outwardly from it. So it's going to be directed outwardly and in all directions from that positive charge. And in that case, these lines over here, we are going to refer to them as the electric field lines. Now if we consider a single negative charge, minus Q, in that case, the electric field is also going to be directed in all directions. However, in that case, the electric field now is going to be directed inwardly rather than outwardly from the charge. So over here, the electric field is going to be directed inwardly into that negative charge. So in that case, if we consider that we have a dipole, let's say we have a positive charge placed next to a negative one. So we have a dipole over here. In that case, the electric field is going to be directed from the positive charge towards the negative one. And as we can see, as we move away from the center, the electric field lines, they start to actually bend. So on and so forth. And like I said, regarding the directionality of that electric field is going to be directed from the positive charge towards the negative one. So over here, the electric field is directed inwardly into that negative charge. Now, there is a notion that you should pay attention to it, which is the difference between the electric field lines and the electric field vector. The electric field lines, they are actually fictitious lines, and their purpose is actually to indicate the presence of the electric field region around a certain charge. Whereas the electric field vector is actually a vector quantity, meaning that it has a direction and it also has a magnitude. And the direction of the electric field vector in that case is going to be tangential to these electric field lines. So over here, let's say if you want to represent an electric field vector graphically, you are going to draw it by being tangential to these electric field lines, and of course it's going to be directed from a positive charge towards a negative one. So it's always going to emanate from a positive charge. Now regarding the magnitude of the electric field, we have seen previously that the electric field is actually a function of 1 over R squared, which is given mathematically as E equal to 1 over 4 pi epsilon 0 Q over R squared. And we have said that the electric field is going to vary with distance. So as you move away from the source charge, the intensity of the electric field or the strength of the electric field is going to decay. So let's say, for example, if we pick 4 different points. Let's say we have point A over here, we have point B over here, and we have point C, which is located over there. Let's say you want to find the electric field at point A, and you want to represent it graphically. So let's say E at point A is actually equal to 10 newtons per coulomb. So in that case, you are going to choose a certain appropriate scale for that value. Let's say each 1 centimeter corresponds to 1 newton per coulomb. And then you are going to draw over here a segment which is going to correspond to EA. And of course, EA, it has to be tangential to these electric field lines. Now let's say you want to find the electric field at point B. And let's say that the electric field at point B is actually equal now to 7 newtons per coulomb. So as we can see now, the strength of the electric field decayed as we have moved further away from the charge Q. Therefore, in order to represent the electric field at point B graphically, you are going to represent it in terms of a shorter segment. So the segment is going to be shorter than EA over here. So by using the appropriate scale, you are going to draw over here a shorter segment from EB. And then the same logic at point C, which is located further away from Q. And let's say that the electric field at point C now is equal to 3 newtons per coulomb. Therefore, you are going to represent the electric field over here in terms of a much shorter segment. So as we can see, as we move away from the source charge, not only that the intensity of the electric field is actually decaying, but graphically we are representing the electric field each time in terms of a shorter segment. So depending on the value of the electric field, you either represent it in terms of a lengthier segment or in terms of a shorter segment. So simply you have to pay attention to that notion, which is the distinction between the electric field lines, which are fictitious lines, and the electric field vector, which is actually a vector quantity, meaning it has a direction and it also has a magnitude. Now moving on to the last part in our topic of today, which is the equipotential points. What are the equipotential points? The equipotential points, they are points that have the same electric potential, meaning the same voltage. So the equipotential points, they are points that have the same electric potential, or simply the same voltage. But here you have to keep in mind one thing, that the electric potential is actually different in terms of scale when it comes to comparing it to the electric field vector. For example, the electric field vector is a vector quantity, meaning that it has a direction and it has a magnitude. Whereas the electric potential or the voltage is actually a scalar quantity, meaning that it only has a magnitude but it doesn't have a direction. Now let's consider that actually we want to map a certain electric field region and we want to locate several points that have the same electric potential. So we want actually to locate equipotential points. So let's consider that we have the following positive charge. As we have seen previously, for a positive charge, the electric field is going to emanate outwardly and in all directions from it. And let's consider that actually we want to map that region in order to locate several points that have the same electric potential. So using a probe, which is actually a voltage detector. A probe will be connected to a voltmeter. It has like a metal tip, and then by placing that probe on a certain conducting paper, you will be able to locate the points that have the same electric potential by reading their values on the voltmeter. So let's say that we start mapping that region, but before we start mapping, let's consider that the main voltage of that source charge over here is actually 5 volt. So that source charge over here has a certain voltage of 5 volts. Now as we start moving away from that source charge, that electric potential is going to decay, because the electric potential in that case is going to be a function of 1 over R. The electric potential is by definition given as the work done on a charge in order to move it from one potential point to another potential point with respect to that charge itself. And the work, we know that it's equal to the force times distance, so F times R over Q, and that force over here is none other but an electric force, which we have defined it previously to be 1 over 4 pi epsilon 0 times Q1 times Q2 over R squared. So that equation over here becomes the voltage equal to 1 over 4 pi epsilon 0 times Q times Q prime over that Q over here and times the distance R over R squared. So first off over here we can simplify Q and Q. Then we can simplify R and R squared, and we are left with the voltage equal to 1 over 4 pi epsilon 0 times Q prime over R. And that would be the final expression for the voltage, which is actually dependent on 1 over R, meaning that it depends on distance. So whenever you move away from the source charge, that voltage over here is going to decay. So going back to our example, let's consider that we are mapping that region around the charge, and we find out that the following points, they have the same voltage or the same electric potential, which is 4 volts. So the voltage started to decay. Then you map that region over here, and you find out that the following points, they also have the same voltage, which is now at 3 volts. And in a similar manner, let's say we have moved further away from that charge, and we find out that the following points also have the same electric potential, which is of 2 volts. So as we can see, as we are moving away from Q, the voltage is decaying. Now what would happen if we actually connect the points that have the same electric potential together? So for example, let's say we are connecting the points that have the same electric potential of 4 volts altogether. In that case, you are going to be defining the so-called the equipotential lines. So what are the equipotential lines? The equipotential lines, it consists of points that have the same electric potential. So by joining these points, you will be forming the equipotential line. In a similar manner, if we connect these points over here, you will be also forming another equipotential line, which is of 3 volts. And by joining these points over here, you are also going to be forming another equipotential line, but this time which is of 2 volts. And you have to keep in mind over here that the separation between these lines is not actually equidistant, simply because over here the voltage is a function of 1 over R. So the separation between them is not going to be equidistant. Now regarding the equipotential lines, the equipotential lines, they have 2 important properties. First off, the equipotential lines, they are always perpendicular to the electric field lines. So over here what we have actually is we have the electric field lines. So as a first property, the equipotential lines, they are always perpendicular to the electric field lines. So over here at each point of intersection, these lines are actually perpendicular to each other everywhere. That would be property number 1, which is that the equipotential lines are always perpendicular to the electric field lines. The second property would be, let's consider that at that point over here, let's call it point A, you have a certain charge Q. And you want to move Q from point A, let's say, until point B over here, where the separation between them is actually R. So we are moving Q from point A to point B along the same equipotential line, which is of 4 volts. In that case, the work required in order to move Q from A to B along the same equipotential line is actually 0. So the work is equal to 0 whenever you want to move a charge along the same equipotential line. So no work is required in order to move a charge along the same equipotential line. So that would be the second property. So the first property would be that the electric field lines and the equipotential lines are perpendicular to each other. And the second property would be that zero work is required in order to move a charge from one location to another along the same equipotential line. However, if you were to move Q from point A to a certain point at a different equipotential line, therefore the work is no longer zero over here, but rather you need to have a certain work which is done by the electric field in order to move Q from point A to point B. Now let's try and prove these two properties over here. The fact that the electric field lines and the equipotential lines are perpendicular, and the fact that the work is actually zero. We know by definition that the difference in potential between 2 points is given as delta V equal to the work done on what? The work done on a charge to move it from one equipotential point, from one potential point to another per unit of that charge. So delta V is equal to the work done on a charge, on that charge, to move it from one potential point to another with respect to Q. So delta V is equal to the work over Q. Therefore, the work is equal to Q times delta V. So moving on from that equation, delta V is what? Let's consider that we want to find that potential difference between point A and point B, which are situated along the same equipotential line. So we know that VA is equal to VB, which is equal to 4 volts. In that case, delta V, which is equal to VB minus VA, is actually equal to 0 volts. So since delta V is equal to 0, therefore, the work done in order to move that charge from one point to another over here is actually equal to 0. And therefore, we have proved that the work done on a charge along the same equipotential line, or to move the charge along the same equipotential line, is actually equal to 0. That would be the first property. Now the second property, which is to prove that the equipotential lines and the electric field lines are actually perpendicular to each other. So the work over here, it can also be defined as the force times distance. So the work, by definition, is defined as F dot R. And F over here would be the electric force exerted on a charge times distance. And that electric force, we have defined it previously in terms of the electric field to be E equal to F over Q. Therefore, F is equal to Q times E, Q times the electric field. Therefore, that equation over here becomes the work equal to Q times E dot R. Therefore, the magnitude of the work would be Q times the magnitude of E times the magnitude of R times cosine theta. And theta would be what in that case? Theta would be the angle which is formed between E and R. So over here we have a dot product. The dot product would be the magnitude of the first parameter times the magnitude of the second parameter times cosine of the angle formed between that. So theta is actually equal to the angle which is formed between E and R. Moreover, we have proven previously that the work done between A and B, so the work done between A and B over here along the same equipotential line is actually equal to 0. So that entire quantity is actually equal to 0. However, the Q over here, the charge Q, it has a certain magnitude, a certain strength. Therefore, Q cannot be 0. The electric field, it also has a certain strength. Therefore, E also cannot be 0. And R over here, which is the separation between A and B, it also has a certain value. So also the parameter R, it cannot be 0. Therefore, we are left with the fact that the only parameter in that equation which is actually equal to 0 would be the cosine theta. Therefore, we deduce that the cosine theta is actually equal to 0 in that equation, which is an indication that theta is equal to pi over 2 or equal to 90 degrees, because cosine pi over 2 is actually equal to 0. And over here we have proven what? We have proven therefore that theta, which is the angle formed between E and R, is actually a right angle. So in that case, we have deduced that the electric field E is actually perpendicular to the separation R. Moreover, the electric field over here is along what? The electric field is actually along that electric field line. As we have seen before, the electric field vector is actually tangential to these electric field lines. And R is actually along that equipotential line. So E and R over here, they are perpendicular to each other, and therefore the electric field lines are perpendicular to the equipotential lines. And therefore, we have proven these two properties, that first, the work done on a charge to move it from one point to another along the same equipotential line is actually 0. And the second property that we have proven is that the angle formed between the equipotential lines, between the electric field lines and the equipotential lines is actually a right angle of 90 degrees. And that would be it for the equipotential lines and the electric field method.